Okay, so today we are going to talk about increase, decrease, boundedness, local, and absolute extrema. So the first thing we're looking at is some definitions. So we have here a function f is increasing on an interval if for any 2 points the interval has a positive change. Okay? A function f is, we have now decreasing on an interval if for any 2 points in the interval a positive change in x results in a negative change in f of x. So our big difference here is, well, they maybe both have positive changes in x. The difference with an increasing function is we see still a positive change in f of x. For a decreasing function, you have a negative change in f of x. Then a function f is constant if for any 2 points in the interval we have a positive change resulting in a zero change. So as you're listening to these words, I want you to think slope. This is very similar to slope. Okay, so if you have an equation that would be increasing, you'd have a positive slope. If it was decreasing, you'd have a negative slope. And if it was a constant horizontal line, there's zero change or zero slope. So we're going to graph these, and it says for each function, we're going to tell the intervals on which it is increasing and which it is decreasing. So if we look at the calculator, and we go back to this graph, here's our graph, x plus 2 quantity squared, and I can see as I'm watching my graph, and I want to think, read the y values, watch my y values as they decrease, but tell me the x values and when they're happening. So I can see my y values are decreasing, starting all the way out, negative infinity, and they are decreasing all the way until I get to the negative 2. So I'm looking at this again, reading my y values, but reporting the x. So on the x-axis, negative infinity to negative 2 is where my y values are decreasing. So I can say decreasing negative infinity to negative 2. And now we're going to include negative 2 on this. And now if I come back out again, I read the y's, but report out the x's. So if I'm reading my y values, I see, okay, my y values start to increase again at that negative 2 value, and they're increasing for the rest of the graph. So I'm going to report the x values that it happens on. So from negative 2 out to positive infinity, I can see my function is increasing. Okay, so again, hard bracket, negative 2 to infinity. I want to include that. So it might not be a bad idea to maybe make that note to yourself. You want to think, read the y's, report the x's. If we go to letter B, here's our second graph, same idea here. Now this one might be a little bit more difficult to see, and this may be a place where you want to go to your table and take a look at the values and see what's going on. Now we see an undefined value at 1. That's something you want to keep in mind. And if we scroll up the table, I can start to see, well, what happens, right? Well, I want to read my y values, but I want to report my x values. Well, if I'm looking at my y values, starting at a negative side, I see my y values are constantly increasing. Slow, but they're increasing. And they keep increasing until I hit that asymptote. Okay. And then if I look at the graph, again, I can see what's going on the graph. My graph is still increasing from that negative 1 value, it looks like, to 0. So when we write that interval, we're going to say, okay, the function is increasing. I report the x's. Negative infinity up to negative 1. Now I can't include negative 1 because there's an asymptote. I'm going to include that with now negative 1. Again, soft bracket on both because of the asymptotes. Out to 0 because again, we want to include that point when we're talking increase, decrease. Now if we go back to the decrease section, we're going to start right at that 0. So starting at that 0, I can start to see the graph is decreasing. Again, we're going to have an asymptote at 1. And then if I pick it back up on the other side of 1, it's going to continue to decrease all the way out to positive infinity. So again, start at 0, go to 1, and then I'm going to pick it back up on the other side of 1 and go out to infinity. Okay, and so now we're going to move on to the concept of being bounded. Lower bound, upper bound, and bounded, which basically is saying it's both bounded above and below. And when we're thinking of above and below, again, the y-axis, we're looking at the y-axis on this. And I want to see if my graph has a bottom that it's not going to go beyond or a top that it's not going to go beyond. So we're going to graph this first one, this first equation. We have 3x squared minus 4. So here's 3x squared minus 4, and as I look at this equation, I can see, well, looks like a parabola, and there's definitely a bottom to it, meaning it's going to be bounded below. There's a limit to how far down on the y-axis that graph is going to go. If you look at the top of the graph, however, it keeps going up, 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 up. There is no stop, so I can't say anything about it being bounded above. So the only thing I have here is bounded below. In our second graph, we take a look at that one. Well, now we have something different, because now not only does it stop at the bottom, it's not going to go beyond that minimum value, but it's also not going to go up above the maximum value. So in this situation, not only is it bounded below, it's also bounded above. So you could answer this by saying bounded. If you wanted to state both below and above, also okay. And then on the back, we're going to have a discussion about local and absolute extremas, so maximum mins. And when we look at this, we want to think there's a slight difference between a local and an absolute. Local meaning it's either a maximum or a minimum, but it's not the absolute. It's not the tallest. It's not the greatest. So meaning there's a turning point and it changes. So let's take a look at a graph. So this is that graph that they have given us in that example. We have to decide if it has any local or maximums or minimums, and perhaps any absolutes. And so if we look at this graph, I can see the very first number that we are looking at down here is at negative 25. And the graph, we can call this bounded below, slightly below. And I see it has what is a minimum, and I see that there is nothing else below this point. So that takes that and makes it not only a minimum, but an absolute maximum, meaning it is the lowest of low. So I could say here, we have an absolute minimum, and that absolute minimum occurs at negative 24.1. Notice that's the y value. We can state here when x is equal to 2.06. Okay? If we go back to the graph, we have another minimum. It's another low value. We're going to look at that coordinate 1.6 and negative 1.77. It is not the lowest of low, but it is a low point. So we can call that a local minimum. So we can write that and say local. It's a local min. Now again, you're going to tell me the y value that it happens at. It happens at a negative 1.77 when I see my x value is about 1.6. And again, our maximum, so I see a maximum. Now, it's not the tallest point, because my graph keeps growing up, up, up. Therefore, we can't say it's bounded above. So it does have a maximum value. It's just not an absolute. So for that one, we would have to call that a local. So we have here a local maximum. And we can say that happens at 1.32. And again, we're going to state, now that's the y value. Tell me at the x value that occurs. So that occurs at 0.456. So we have local, we have absolute. Local is somewhere in between the function, absolute being the lowest of low or the highest of highs.